Good morning, Astronomy 1010. Welcome to our 11th lecture, where we will transition from terrestrial geology and into planetary atmospheres. This week, this Thanksgiving week, it's all planetary atmospheres. And there's a lot to talk about. This will also help us transition into the outer solar system, where planets lose their solid surfaces and become, well, somewhat balls of gas, as you will see. But basically, the gas giants are so named because they are mostly planetary atmosphere. Therefore, the stuff we talk about today, while designed to talk about terrestrial planets, does carry over to the Jovians. I also have a couple of fun announcements that may please you. I built in a little pressure valve for this week because I know things are getting real. Assignments are due. Turkeys are being quietly cooked in our homes without our families. This week, we're not going to have a lab, so no lab today, just a lecture. That ought to make you happy.
Oh, that totally stinks because I wrote everything out last night.
Oh, really? For which lab? Because I think it
Lab
says,
11.
well, then it'll be all ready for next week, won't it, Andrew?
Oh, that's awesome.
It'll still be useful. So you did not extra work. You did the work. Hello, Cam. That will help you for next week, and then you get a little bit of you get a little break in the action here. As to Wednesday, I know it's the day before Thanksgiving. We are, of course, going to have a lecture on Wednesday. I'm still debating about whether or not we'll do homework on Wednesday. There is an assignment. We are supposed to do a homework. I may decide not to. We'll see. Anything's possible, guys. Stay tuned for more, okay? All right, so let's talk about planetary atmospheres. First thing I want to do is I want to share screen, and I actually want to go back to our terrestrial lecture for a second, and I want to look at our 4+1 terrestrial planets on slide 2. What are we going to talk about when we talk about planetary atmospheres? Now, listen, guys, I know what you don't know, but I don't know what you do know. So I need you guys to tell me, which of these planets do you think have atmospheres in the first place?
Earth and Venus.
I'm sorry, say that again, Noah?
Earth and Venus.
And one more.
Maybe Mars.
That's right. Mars has a thin but substantial and real atmosphere. So today, when we start learning about terrestrial atmospheres, for those of you who did not know what Noah shared with us there, we're basically excluding Mercury and the Moon from our discussion. We will be focusing on these guys, Venus, Earth, and Mars. So that's something we should kind of start with. I should mention to you that Mercury, while it's mostly, how should I say this, airless, while it's mostly without atmosphere, there are some very trace gases in the form of, I don't know, sodium atoms that bounce around the surface of the planet. So I will tell you that in professional circles, there are planetary scientists who study Mercury's quote unquote atmosphere. But as far as we're concerned, these gases are of such incredible low density that they're essentially the same thing as the vacuum of space. So I'm just mentioning this in case you ever do read a newspaper article about scientists studying atoms bouncing around the surface of Mercury. These atoms are close to or below what you would consider the best terrestrial vacuums on Earth. So for the most part, Venus, Earth, and Mars are what we talk about when we talk about a significant atmosphere. And what a significant atmosphere means is that it alters and it shapes the fundamental geology of a planet in some way. And that is true on Venus, Earth, and Mars. Atmospheres play a role in the heating and cooling of the surfaces, and they play a role, of course, in erosion, which is one of our geological processes. And you'll remember the dust devils that we discussed at the end of last week's lecture. In any case, why don't we get started talking about the compositions And we're going to take notes on this in just a second. We'll start with our slideshow. We'll start with our planetary atmospheres slideshow here. Come on, you stoopy. There we go. All right. Hopefully you guys can see this. Can you see this picture of clouds above Earth here? Okay, good. And here's our compositions that we really ought to write down on the board because, as you might be able to guess, this is testable material here, okay? So let's go ahead and go to speaker view. Let's click on me. Hopefully this is readable. Hide some of our fun lights. Terrestrial atmospheres. We got notes to take. We have Venus. We have Earth. Sorry, still looking for that marker. And you know what? I think it's time for a fresh one. Venus, Earth, and Mars. Hold on, guys. Stuff is hard enough to read when the markers are good. Okay. So the greatest composition to the atmospheres of Venus and Mars is carbon dioxide. So we have CO2, and that's to the tune of, let's see here. So what is it? Something like 90%. Here we go. 96%. Sorry, I'm having a brain aneurysm there. 96% of Venus's atmosphere is carbon dioxide. The next biggest constituent is diatomic nitrogen, maybe 3.5% or so. And then the remaining 0.5% are, well, what we would say are trace gases, probably some, I'm not sure if the acid rain even makes up 0.5%. It's probably some much lower percent than that. But I wanted to throw that up there to remind you guys that Venus has some acid rain clouds, some clouds that melt metal. You know, like if you've ever seen the movie Aliens 2 or something where the blood from the aliens disintegrates spacecraft, that kind of a very caustic metal-eating acid. And we can talk about the origin of that hydrosulfuric acid in Venus's atmosphere. It does not bear much resemblance to the atmosphere of Earth. I'm going to get rid of the rain part, okay? So Earth, its primary gas is diatomic nitrogen. And that's 77% of our atmosphere that we're breathing right now. Oxygen, which you need for respiration, makes up only 21% of the gas that you breathe. And, you know, let's see here, 98. The remaining, let's make sure I don't screw this up, guys, because I'm, so 21%, 1% argon. Argon is a noble gas. And even though the book does not list them, I think it's a good idea for us to talk about two other very important molecules that play a big role in our planetary atmosphere. The first, of course, is water, H2O, which makes up just under 0.5% of our atmospheric gas. And then there is the all-important carbon dioxide. Carbon dioxide makes up 10 times less than the water. And yet, although it's only 0.04 of a percent. What's that background chatter? Who can't handle hit mute? Let's find the trolls. Okay, where are you, trolls? Did you get yourself? Okay, yeah. Video settings. Hide the trolls. Okay. Carbon, that's okay, Gianna. Carbon dioxide makes up 0.04%. And yet, even though I didn't get into the weeds with Venus's atmosphere on this, you can see the fact that I'm putting it up there means this microscopic quantity of carbon dioxide plays a huge role in our planetary atmosphere. Now let's flop over to Mars's atmosphere and see how the situation changes. Once again, just like Venus, carbon dioxide makes up the primary gas, 95%. Diatomic nitrogen, which we see in all three atmospheres, makes up about 3%. And argon, this noble gas, maybe 2%, something like that. In fact, superficially, Venus and Mars look like they have almost the same atmosphere, minus the acid rain, I suppose. And yet, this atmosphere and this atmosphere are very different from each other in one very important respect, and that is in their thickness, okay? So let's write down up here, Venus has an incredibly thick atmosphere. Earth has a medium thickness atmosphere, and Mars has an incredibly thin atmosphere. In fact, I'm going to tell you a statistic that I read about in one of my graduate texts that made a big impression on me, and perhaps it'll make a similar impression upon you. If you could travel to Venus with a giant vacuum cleaner, and you could just suck up all of that carbon dioxide, that thick, overbearing carbon dioxide atmosphere, if you could slurp it up and then leave only the 3.5% nitrogen behind, that nitrogen atmosphere would be equivalent in both mass and volume to Earth's 77% nitrogen. Think about what that means. This atmosphere and this atmosphere, these gases, it's the same total quantity of gas. Venus has an Earth-sized atmosphere burrowed underneath the 96% CO2. The pressure at the surface of Venus is hundreds of times the pressure at the surface of Earth. There is maybe 100-fold greater amount of gas. It's a little goofy to analyze because the masses of these two molecules are not identical, but you see the point that I'm making, right? Venus, it looks like, oh, only 3.5% is nitrogen until you realize that's the equivalent of Earth's atmosphere with all the CO2 on top. In fact, that becomes our first planetary science mystery, or let's say our planetary atmosphere mystery. Remember that a planetary scientist is similar to Sherlock Holmes. We arrive in the crime scene 4.6 billion years late, and we start trying to figure out who did what in the library. Okay, so the first planetary mystery that I'd like to point out is this. We can see CO2 makes up the primary gas of Mars and Venus. And that's not unsurprising, because we get CO2 from, wait for it, volcanism. Carbon dioxide is the primary gas that comes out of volcanoes, which we studied last time. And if planets do not form with their atmospheres, if they have to build them up over time through volcanic outgassing, it makes sense that the primary gas on Venus and Mars should be CO2. Here's your first mystery. Where is Earth's CO2? How did Venus, sister planet to Earth, pump out a huge obnoxious amount of CO2? And today on Earth, it only makes up 0.04% of our atmosphere. Oh, and by the way, let me add to this mystery for you guys a little bit here, right? Remember that picture I showed you of those volcanoes erupting, like Pintabo in the Philippines or Mount Hood over Oregon? Where's those damn volcanoes here? Remember this picture here? Number 50? Oops. Remember this picture? Guess what that gas is mostly comprised of? CO2. Even today, as our volcanoes erupt, they're mostly CO2 and some water. So why are the two primary gases coming out of volcanoes so microscopic on Earth today? That's planetary science, planetary atmosphere mystery number 1. Here's planetary atmosphere mystery number 2. What the hell is up with 21% diatomic oxygen? This is just dang weird, because although you may not have taken a chemistry class, let me tell you something that it might be easy for you to believe. Oxygen is an explosive gas, okay? It's an explosive gas. It causes combustion. Because oxygen is so violent and so reactive, you don't tend to build up shitloads amounts of oxygen just floating around in your atmosphere, right? This is not a primary gas that comes out of volcanism. And you want to know why it's not a primary gas? Because oxygen is so reactive that it's just likely to react with the rocks and form silicon dioxide. Remember when we talked about what a rock is? 72% of most granite is silicon dioxide. The oxygen will bind to anything. Rock, the hemoglobin in your blood, whatever. So how do we get a buildup of, does anyone know the answer to that question, by the way? Because the answer is very interesting. Anyone want to take a guess where we get our 21% oxygen?
From like the jungles and forests, maybe?
You're not wrong. It turns out that the jungles and forests, was that Jake I was just listening to there?
Yeah.
You can see all of you at once. Where's Jake? Oh, are you hidden from? Oh, there you are, Jake. Jake, it turns out that the greatest contribution to oxygen is life. So you are correct in that sense. I would have naively thought that jungles and forests and trees would be a big part of Earth's oxygen budget. But it turns out that a much greater percentage of oxygen production on Earth does not come from jungles and trees. It comes from cyanobacteria or blue-green algae. Have you ever heard about that stuff before? You can see these.
I've heard of it, but I don't know much about it.
Well, I'm not sure if I know much about it either, but I know that these algae produce photosynthesis, just like forests and trees do. And because oceans cover such a large fraction of the surface of Earth, there's a ton of blue and all waterways combined. There's a ton of blue-green algae out there, and they actually contribute like 80% or more of the oxygen budget of Earth. That's kind of crazy. You could actually cut down, I mean, I wouldn't recommend this. They would probably be bad in many other ways, but you could cut down every tree on Earth like the Vikings did in Iceland, and the cyanobacteria would probably still produce enough oxygen for the animal needs on Earth, which is kind of wild to think about. So that's right, Jake. The answer to this is life creates oxygen. And building up oxygen in a planetary atmosphere is kind of considered a signature of life. Oxygen doesn't get there usually unless some creepy crawlies helped produce it. Let's have one other discussion. So remember, we have two planetary mysteries. Where the CO2 at, that's mystery number 1. And the one that you just kind of answered, Jake, is where do we get our oxygen from? So I've got one more point to make that I think is an interesting point. Why don't we look at a picture of Earth for a second? Here we go. Suppose you came to Earth as an alien from another solar system, and you're flying around in your space shuttle or whatever it is, and you come across an what do they call it in Star Trek, an M-class planet with an atmosphere and potentially habitable aliens, and you look at the atmosphere of the planet with your eyeballs and you attempt to analyze its chemical composition. If you were to look at Earth's atmosphere from above and analyze its chemical composition, what would you assume would be one of the most important gases that makes up our atmosphere? What's the first thing that you see when you look at maybe I need a better picture of Earth here. Let's do this better. you stupid Google. Here we go. That's a nice picture. That's the picture I should have, which I think is the same picture I have, just lower resolution. What would be the first thing you noticed when you look at the atmosphere of Earth?
The clouds,
Which are made of, keep going, Jake.
H2O.
So you would assume that H2O would be the most abundant
The big
gas in our
part.
atmosphere, or at least one of the most abundant, right? And yet,
Mhm.
Jake, what fraction does it make up again?
0.4%.
You just learned an important lesson about planetary atmospheres. What you see is not what you get. Trace amounts of molecules, like the smallest little bit of salt in your atmosphere, completely changes the color and the perception of it. Do you guys know anything about CO2? What's CO2?
Carbon dioxide.
And on Earth, where do we encounter that? Like, have you ever like made dry ice cream or anything like that? Have you ever seen dry ice? That's basically frozen CO2, right? What color is CO2? When it,
White.
yeah, when it's condensed in frozen form, it's kind of white. So for those of you who don't know your chemistry, CO2 is one carbon with two oxygens on it. Let's see if we can find a picture of dry ice. So sure enough, when it's frozen, it's certainly, you know, it's certainly white. But as it sublimates, it kind of just turns into colorless nothingness, unless it's really dense. Carbon dioxide is clear. Remember that Venus is 96% CO2, but what color are the cloud tops of Venus? Oh, shoot. This is a true color picture of Venus here. While they are kind of whitish in some ways, they're also kind of yellowish. Like if you look at Venus through a small telescope, it looks like a yellow disk, a little yellow disk. So all of the coloration that you see in the clouds, it's not from CO2. Obviously, nitrogen is clear. Otherwise, you wouldn't be able to see my face, right? Nitrogen is a clear gas, at least at these concentrations. So the fact that Venus has these yellow clouds, it's all these trace gases that are making up the. Do you guys see my point? The book puts it this way. The book has a phrase, minor ingredients matter. Oftentimes, the minorest, smallest ingredients completely affect the coloration and perception of how a planet looks. And you'll see that's true for the Jovian planets as well. Okay, Andrew, everyone, do you have this down? I think I've made my point there about
Yes.
of atmospheres. All right. Obviously, if we're going to talk about planetary atmospheres, we're going to have to go back and we're going to have to think a little bit about that good old-fashioned ideal gas law. We kind of can't move forward unless you guys remember some things about how the ideal gas law works. So let's erase here. Tell me what you guys know about the ideal gas law. It's an equation, right? We studied it when we learned about the gases that make up the sun. Anyone remember the equation by any chance? I'll forgive you this one time if you don't, but. P equals NKT. What do these symbols mean? No?
P is pressure.
Okay. Noah, what units do we measure pressure in?
I think pascals.
Excellent. You make me proud, son. Always remember that atmospheric pressure, 1 atmosphere of pressure, which is basically sea level on Earth, is 100 kilopascals. Any grease monkeys out there that know what it is in pounds per square inch? You know, if you're like working in a auto body shop, you might have to fill up tires and stuff. So sometimes car mechanics know this.
PSI.
Yeah, PSI. What's atmospheric pressure in PSI? 14.7 pounds per square inch. Not that you need to know that, but I just thought maybe someone did. Okay. Anyways, pressure, pressure, remember, is kind of like the force of the molecules. It's the force of the molecules pressing against each other. N, I'll help you out with, is the number density, often measured in particles per cubic meter, which can also be written weirdly as m to the minus 3. If you want to flip your unit or your variable from the bottom to the top of an equation, you just have to put a negative on the power and that works. Particles are not a real unit. K is the so-called Boltzmann constant associated with gases, 1.4 times 10 to the negative 23 joules per Kelvin. That's the Boltzmann constant. T, of course, is temperature. We can measure temperature in units of Kelvin. And temperature measures something like the speed of the particles. Technically, it's the kinetic energy, but I like to lie a lot, so speed of the particles works for me. When we first learned the idea, well, hold on, let me stand out of your way and sip water while you guys take notes here. Obviously, we have to remember the ideal gas law if we're going to study planetary atmospheres. Now, let's go grab that little cute animation I have somewhere. Boop. And let's see here. Physics Java apps. Come on, buddy. Gas properties. I want you guys to think about this little Java application here. When we often learn about the ideal gas law, we often start off with particles bouncing around inside of a box. You want to know what's weird about planetary atmospheres? There's no box, right? This is what a planetary atmosphere is like. What do you see happening to the gas particles when I open up the box?
It floats up.
They boil away into space. Why isn't that happening with our atmosphere? Why doesn't our atmosphere just go poof and fly away into space?
Because of the effect that keeps the heat of the sun in. I forgot the specific name for it right now.
No. The heat of the sun is bad. That's going to make the molecules have thermal energy and boil away even faster.
Is it gravity?
Thank you, Noah. It's gravity. This box does not have gravity. Ooh, it's got a little gravity lever. Let's do that. Pump, pump. Now I want you to watch the gas particles when I add the gravity. I'm going to add the gravity. I'm going to open the box, okay? Boom. Okay, so tell me what's going on here.
They're bouncing around and out.
Not too much. For the most part, the particles are too massive to bounce away. Every now and then one gets out, but for the most part, most of the gas particles are staying. gravity is in balance with pressure. What's the name for this? I think it's called hydrostatic equilibrium, right? Hydrostatic equilibrium. Suppose one took a hot air balloon journey from the ground up into outer space. Do you think the pressure would stay constant? Do you think the density of the gas would stay constant? Hold on a second here. Let's get out of this slideshow. What if we wanted to measure the properties of the ideal gas law as we took a hot air balloon from the ground into outer space? Let's create a graph, a famous graph called the density scale height of our planetary atmosphere. And creating and analyzing graphs are an important part of your scientific training. The way we normally make well, actually, maybe I should ask an even more basic question that probably most of you don't know. How high does the atmosphere extend? How far up do you have to go in kilometers before you reach outer space? Does anyone remember the height of the International Space Station? No, that's all right. How tall is Mount Everest? How high up does an airplane fly? Do you guys know things?
Oh,
You're
I
getting-
know it. It's 400,000 kilograms.
Wait, that's the mass of the ISS, Andrew.
Oh,
Wait, we got two Andrews. God damn it. Okay. Here, let me just tell you the answers to these things, okay? Mount Everest is 9 kilometers tall. An airplane, which I cannot draw.
or wait, is it? Oh, I think I know the kilograms.
No, I'm not asking kilograms. I'm talking about height. Kilograms are a unit of mass. I wanted to know, like, where does the atmosphere end, right? Like, obviously, if you climb up to the top of Mount Everest, the oxygen thins out, but you still have atmosphere. An airplane flies at 10 kilometers. The International Space Station has an orbital height of 400 kilometers. Now look, the ISS has to make rocket thrust corrections once per year due to atmospheric drag. But come on, give me a break, right? If you go up to the ISS, did you guys see those astronauts that just went to the ISS? Did we talk about that? It's been in the news. They launched another Dragon capsule. Let's click on the news here. SpaceX NASA Crew 1 mission docks with ISS for a 6-month stay. Let's see if they have a picture of them docking there. I don't know about y'all, but this shit looks like outer space to me, okay? Like, let's get another picture of the ISS. Look, some people might say this is in the atmosphere of Earth, but they don't call it the International Atmosphere Station. They call it the International Space Station. Basically, there's such a small amount of gas up there that there's nothing left. You're basically in outer space once you get to about 400 kilometers. So this is an airplane, or this is a hot air balloon ride from the ground up to the top of our atmosphere. And let's plot on the x-axis the density, the mass density of gas particles in kilograms per cubic meter. When you are at sea level, which is where you are in the ocean state, that's Rhode Island for anyone watching this outside of our class, the density of gas is 1.2 kilograms per cubic meter. which is actually kind of wild to think about, right? Like, you think that air is weightless or massless, but if you take a cube roughly this big, this is more impressive when I do it in the classroom, a cube of air that's roughly the cubic dimensions of this board here, okay? This board is about 1 square meter. If you made this board into a cube, that cube of air has the equivalent mass of one of these. And let me tell you, this is something you wouldn't want dropped on your head, okay? So you don't realize it, but there is a mass and there is a weight to air. What do you think the density of air is when you get to the International Space Station? In theory, it should be what's the density of air in outer space? This is a tricky one.
0.
Yeah,
0.
fucking 0. There's no particles there, right? Okay, all right, sorry. Pardon my français, okay? 0 kilograms per cubic meter. That means as I take my hot air balloon ride, now I want you to go on a mental journey with me. I've got to get from this point here, 1.2 kilograms per cubic meter, to this point here, 0 kilograms per cubic meter. Now I can think of 3 different ways for that graph to go. See if you can go on this journey with me here. The first way would be what we would call a linear drop-off. A linear drop-off is where with each kilometer I go, I lose more and more gas. So this is 1. This is what we would call a linear drop-off. Another possibility, let me remove my badly drawn airplane here, is what we would call an exponential drop-off. An exponential drop-off drops off, let's see here, quickly at first, and then asymptotes slowly out to nothingness. 2 is an exponential drop-off. And the third possibility is if it bends the other way, which is what we would call logarithmic. It starts off not changing too much at first, and then quickly goes to 0. The whole way science works, students, is for a scientist to consider the possibilities of what will happen if they take some measurements and then try to predict which of the outcomes is most likely. So go ahead and play Baby Scientist Junior here. Which of these 3 possibilities do you think is the most likely way an atmosphere drops to 0 as you go from the ground to outer space? If you had to guess, give it your best shot.
Exponential.
Let's see if Noah's right. Just so happens that I have the real graph with me, Noah. Something to share with you. Damn, you're good. That's exactly what it is. Look at Noah. You start off at 1.2 kilograms. Sorry, let me see if I can flip this thing over here. 1.2 kilograms per cubic meter. By the time you reach airplane height, what fraction of your gas have you lost? What if you had to divide 1.2 by 0.4? Do you know what that is?
3.
Good. So by the time you get to 10 kilometers up, which is the little over Mount Everest height, what fraction have you lost?
A third.
Well,
Or
you've lost
two
2/3,
thirds.
and 1/3 remains, correct? So you've
Yeah.
lost about 66%. What if you go to double that? I think like the craziest, I think some spy planes can go up close to 20 kilometers, but I'm not sure. The atmosphere is pretty thin up there. They might not even be able to make it. I don't know what the highest an Air Force jet can go is. Anyways, 20 kilometers up. What fraction have we lost then?
It's like a 12th. Or
Yeah,
we've
we
lost
lost
11.
11/12, I guess, and there's 1/12 remaining. And by the time you go up to 30 or 40, And people study the atmospheres of planets. All this doesn't seem like much to you. You would consider this outer space. If you were there, you'd be like, I'm in space now. But atmospheric scientists do not consider that outer space yet. They know that there's a lot of physics that goes on in the believe it or not, what we're here to study today is a lot of the shit that goes on at these levels, where there's just small amounts of gas. It has a big role in planetary science. No kidding. Okay, so if we were to consider another graph, what if instead of the density, we measured another property of the ideal gas law? So instead of density, now I'm going to do pressure, which is a related quantity, correct? And same question, we'll ask it to Noah because he was pretty good last time. Noah, knowing what you know about the ideal gas law, would you expect okay, so atmospheric pressure is 100 kilopascals. Noah, what's the pressure of outer space going to be?
0.
Right, you can't have any force of the particles if there's no particles, right? So, knowing what you know about the ideal gas law, Noah, would you expect it to drop off the same, or would you expect it to be any different?
I want to say the same, but I don't know how temperature affects that.
Well, let's leave temperature out of it for a second, although you are asking the right question, believe it or not. Let me show you the real thing. It's the same. Noah, by the time I get to airplane height, let's see, what fraction have we lost there?
70%.
70%, yeah, something like that. And by the time I get to 20, you've lost 90%, right, of the pressure. This is why, you got to have pressurized cabins. If you're flying this high and there's, God forbid, a little hole in the window or something, that pressure gradient can literally suck you out the window. And that's happened to people before. And it's quite unpleasant. So what was that about temperature then? What if we wanted to do this? Now all of the things I've been doing with you, Noah and friends, this is a buildup. All of this was like a tee up for me to drop some knowledge on you, okay? The graph that I really want to talk about is not the pressure scale height or the density scale height. I want to talk about a legendary graph from atmospheric science called the temperature scale height. Obviously, measuring temperature as a function of height is a little tricky because the temperature at the surface of Earth depends upon your latitude. But if we wanted to take a global average of temperature, now here I'm going to cheat. I'm not going to use Kelvin. I'm going to use Celsius. And the average temperature of the surface of Earth is 15 degrees Celsius. What's the temperature of outer space? That's a question for you. What is the temperature of outer space?
Zero again?
No.
Or
What's the
Is it
definition?
like negative?
Pardon?
Is it negative because it's so cold?
No. No. We need to review our fundamental definition of temperature. If I show you an ideal gas in a box, what does the temperature mean? This is an
kinetic
ideal
energy.
gas. I'm sorry, say that again, Noah.
The kinetic energy.
In
the
outer
particles?
space, there are no particles. So what does that mean?
Is there no temperature?
Yeah, it's kind of undefined. If you have a box of nothingness, you can't really define the kinetic energy of the particles, can you? That's your first hint that things are weird. Okay, so Noah, this is your density scale height. This is your pressure scale height. What do you think the graph of temperature is going to look like?
I think it's gonna be the logarithm because it's gonna be undefined once you hit space.
And what if I were to show it to you and it looked like this? In fact, this isn't even the whole graph. Noah, after it does this, let me change it to blue so it looks like it's a continuation. After it does this, it then goes back up again. In fact, I wanted all these graphs to be like the same format, but let me show you a more sophisticated version. This is a legendary graph known as the temperature scale height in our atmosphere. And Noah, it's just fucking nuts. It doesn't follow any of those graphs. Look, as you're going up to airplane height or Mount Everest height, it slowly drops and gets colder and colder. That's why you need that big protective gear at the top of Mount Everest, right? But then look what happens. After 20 kilometers, it starts to go up again. After 50 kilometers, it drops again. After 90 kilometers, it keeps going up and it gets higher and higher and higher all the way into the vacuum. That's kind of weird, right? At each of these switchbacks, Noah, different types of physics is taking place. And this is important because we use these switchbacks as our definition of the layers of Earth's atmosphere, or at least we use these two and this one. Oops, let me try to. Okay, first thing I want to do is just to help you guys. So these are the layers of our atmosphere up here. Let me explain to you why, as you get towards the vacuum of space, the temperature could get higher and higher. As you get further into outer space, the number of particles goes almost to zero, but not quite to zero. What are those particles that are left behind? They're basically solar wind ions. They're pieces of helium nuclei or protons or the occasional gas particle that had just gotten such a kick or a boost from some random collision that they are freaking flying through space. So if you go out into outer space and you try to capture particles, it's basically a big box of nothing, but every now and then, one particle with super high kinetic energy just goes zoom, flying by. So those trace gases end up having pretty high speeds. The temperature of the microscopic gases in space tend to actually be super, super high because they're zooming. Something gave them a kick to get them out there in the first place, right? They didn't get to outer space on a pleasure boat. They got out to outer space because something gave them a good hard kick. Let's see if we can just, I know it's going to be a shitty cartoon version. Let's put this into our, let's try to put something like this into our notes, okay? Because this is the thing that you need to remember. This is how we define our layers of Earth's atmosphere. So first, the temperature drops up to about 10 kilometers, and then it raises and goes up again, and then it keeps launching out into outer space. This isn't a very good graph, but it'll have to do, okay? This is what the temperature of our atmosphere does. Now, this lowest part, let me do this in blue. We're going to define the layers of Earth's atmosphere. Most of the atmospheric gas is contained under this layer, and it's called the troposphere. Then there's the layer where this big bump happens. This is known as the stratospheric bump. This is defined as our stratosphere. Then there's a layer where things start to heat up again. That's the thermosphere. And then the very highest layer of a planetary atmosphere This layer up here is called the exosphere. That's the layer where gases are boiling away into space from time to time. These are the 4 layers of Earth's atmosphere. And just as we started off by defining the layers of Earth's interior and then analyzed other planets in terms of that, you need to memorize these because these are terms that we will use to analyze the atmospheres of other planets. Most of the other planets that have atmospheres, including Jovians, have some versions of these things. In fact, if you have room for a little extra note-taking, these are the layers of Earth's atmospheres. And egad, would they make a great test question. Let's make note of this feature here. This feature is called the stratospheric bump. Andrew, when you're done, let me know, because that'll be a good signal to erase.
I'm all set.
Okay, cool. Well, now, students, if you're the curious type, the question that we need to ask ourselves is, why? What causes the temperature to rocket back and forth like this? The answer, simply put, is sunlight. It's different types of light from the sun interacting with our different layers. I gotta say, guys, every now and then your book gets an information graphic right, and they really got this one right here. They basically made a cool, sexy cartoon graph which shows you the changing temperature scale height graph, but they superimposed upon it the different types of light that are causing them to heat up. Let's start with the bottom layer, the troposphere. Weirdly enough, the troposphere is not exactly heated up by sunlight. And that's because mostly the only light that gets to the ground is actually visible light. And as you can clearly tell from the fact that we can see each other's faces right now, visible light is, or the atmosphere is transparent to visible light. Otherwise, you wouldn't be able to see my nose, right? The visible light does not directly heat the atmosphere. The visible light heats the ground. Notice that the visible light here is going all the way down to the ground, and it's heating up the ground rock. And this is something we really have to stop and talk about. When you step outside on a warm, sunny day, when you feel that sunlight on your body, you get your normal experience of temperature is actually the temperature of the air, right? Like the air in my apartment right now is 72 degrees, and it's actually quite warm. And if you wouldn't mind turning it down to 68, I would be very grateful. Okay, thanks. So, I just started to realize I'm overheating here, and I needed some help from our lovely assistant, Jordan. I'm overheating right now because of the temperature of the air in this room. And if I were to call up, hey, what's the temperature outside? It's probably 54 degrees out right now, and that's the temperature of the air. But when you step into the sunlight and you feel that sunlight heating up your body, you kind of get the mistaken idea that the sunlight is heating up the air, but that's not true. The sunlight is heating up you because you are a solid, dense object like the ground. Sunlight heats the ground. What heats the air then? We got to talk about that greenhouse effect. What heats air up?
The radiation from
From,
sunlight hitting the ground.
say that again, Joel. The radiation from
The sunlight hitting the ground.
Okay, hold on. We have to say this better, but you're kind of right. The visible light hits the ground heats up like a warm rock. The warm rock re-radiates infrared light, and the infrared light heats up the atmosphere. This is the principle of how a greenhouse works. Ever get into your car on a hot summer day and find it's like 5 or 10 degrees warmer in there than it was outside? That's because sunlight's coming through your window, heating up your leather seats or whatever. They're re-radiating back up and captured by those greenhouse gases. And in that little bubble of air, it really starts to heat up. It's the greenhouse effect, right? This means, if you think about it, students, the air is heated by light from Earth, not by light from the sun. Isn't that weird? At least at the bottom layers. At the bottom layers of Earth, that's where the greenhouse effect takes place. Now, we should probably have a greater discussion about the greenhouse effect, but because time is short and life is long, let's quickly look at how the greenhouse effect works. This is only in the troposphere, students, okay? The yellow band represents visible light. It strikes the ground warms up, infrared light comes back up through the air. But here's the difference. Infrared light is not getting absorbed. Let me go to share screen again. The infrared light is not getting absorbed by the nitrogen. It's not getting absorbed by the oxygen, not for the most part. Most of that infrared light is getting absorbed by microscopic trace gases, including H2O and CO2. These are called greenhouse gases because they are wicked, wicked good at absorbing infrared light. These gases are not as good as absorbing infrared light. Believe it or not, if our atmosphere was all nitrogen and oxygen, it would be really damn cold on Earth because we require these microscopic gases to do all of the heating. That's what we mean when we say a greenhouse gas. A greenhouse gas usually has like 3 molecules in it, like CO2. And what happens is, let's look at a GIF here. This should be coming from below, not from above, but you work with the animated GIFs you can find on the internet. So work with me here. Infrared photons strike the molecule. The molecule starts to jiggle and it gets vibrational modes. Usually it mosh pits around and crashes into some air molecules and heats them up. And then the lower energy jiggles re-radiate infrared back out. This is how greenhouse gases work. So why don't we take some notes on each of these layers of our atmosphere about how they're getting heated up. Okay, things I think you should know. Let's start with the troposphere. I would say most of the gas is found here. Also, don't forget, you live here. You would not be comfortable if you took a trip without a spacesuit into the stratosphere. It's heated from below by infrared light from Earth. Let's not forget that the ground is heated by visible light. Infrared light is absorbed by so-called greenhouse gases. And because greenhouse gases are a hot topic, we should list what those greenhouse gases are. They include carbon dioxide, CO2. Believe it or not, water is a potent greenhouse gas. Clouds make the planet warmer. Well, they also make the planet colder by blocking visible light, so it's a double-edged sword. Other greenhouse gases, CH4 is methane. There's some others as well, but these are the most important ones. Guess what our greatest contribution to methane in our atmosphere comes from? Someone's got to know this.
Oh, it's from our garage, right?
From cows burping.
Yeah, they call it euphemistically agricultural products, but that really means cow shit and cow farts and stuff. Okay, so most of the methane comes from things like that, for agricultural outgassing. But methane, I should remind you guys, has an even lower concentration in our atmosphere than either water or CO2. So people tend to freak out a little more about CO2. The water is just part of our atmosphere. You can't fix that because there's a lot of water floating around out there. But the CO2, a lot of it is human produced. And the methane is agriculturally produced, which is still kind of the same thing as human produced. But the methane has a much lower concentration, so we don't freak out quite as much about methane, although some people do. Okay, we're going to come back. Wait, let me get to the right view here. Let's talk about some of the other layers. We'll get back to the greenhouse effect a little later on because I'm doing badly on time here. I'm going to erase. Is that okay?
Oh, wait.
Yeah. Let me know when you're good here, Andrew.
I'm all set.
Thank you. Let's talk a little bit about the stratosphere. If we can get all these layers done, then we'll be set up well for next time. So the stratosphere is home to the infamous stratospheric bump. And I need you guys to think about what it means. The reason why it's called the stratosphere is because there are stratified layers of atmosphere, kind of like the layers that you would see in a birthday cake or something like that. In a normal room, heat flows from the ground up to the ceiling, right? The stratosphere is a region where they call it a temperature inversion layer. Normally it's cold on top and hot on the bottom. But in the stratosphere, what's weird is you have layers of hot atmosphere sitting on top of a layer of cold atmosphere. Now, when you already have segregated your hot and your cold, this prevents any convection from happening in your atmosphere. Because you know how heat rises? Well, if the heat's already risen, it can't rise anymore. And so you don't get any convection. The result is it's a super stagnant layer of the atmosphere that never changes. They call it an inversion layer. So there's no convection. This tends to make thin strip-like layers of temperature. I've heard it described in graduate texts as an inversion layer. And the thing that makes this temperature bump happen is from interactions between ultraviolet light from the sun and a molecule called ozone. Ozone is triatomic oxygen, and it has a wicked, wicked tiny percentage in our atmosphere, and yet plays a huge role in planetary science. First of all, ozone shouldn't exactly be there, but what happens is sometimes your diatomic molecule of oxygen will get sizzled apart by a lightning blast, and instead, oxygens will kind of recombine awkwardly in this molecule made of 3 oxygen atoms, okay? A little triad here. And these oxygens are not quite as stable as they would be in a diatomic form, but they become an excellent absorber of ultraviolet light. And in a cool way, they actually become like a bulletproof vest for planet Earth. Because remember, ultraviolet photons, they're mean and they're nasty and they give you sunburns and they are harmful to life. They also would provide crazy amounts of heating to our planet if we didn't block them. So here comes a super short wavelength UV photon. The UV photon will bust the molecule apart, resulting in 3 oxygens kind of zipping around. Now, they will go mosh pitting and crashing into the nearby molecules, which of course heat up the gas. And then when they lose kinetic energy, they kind of come back together. And this is why it's kind of like a bulletproof vest, because they reform and now they're ready to block another UV photon. Because they sit in the stratosphere, they don't get pushed around too much. They don't get convected out of the game. And they basically can keep absorbing fresh ultraviolet bullets. Okay, let's see what your brains can comprehend here about this layer. Let's see if I can ask you some simple questions and if you can imagine the answers. Notice, students, that as we go from the top of the troposphere up through the stratospheric bump, in this section of the stratosphere, the temperature is rising. Can you guys explain that to me? Why is it getting hotter and hotter and hotter from 10 kilometers up to 50 kilometers? Take a guess.
You're getting closer to the sun.
That's right, Joel. Beautifully put. You're getting closer and closer to your light source, which is the sun. I love it. Very easy, very logical. Now, Joel,
Plus, aren't you picking up the UV rays, which would be more?
Yeah, you're getting closer to the source of ultraviolet light. You're getting closer to outer space. Yeah. Okay, Joel, then riddle me this, Batman. Why does it suddenly turn around and start dropping again?
Because the pressure reduces.
I would say density, because it's the number of UV absorbers or the number of ozone molecules. But
yeah, like with the pressure decreasing so rapidly, the particles are farther and farther apart. So therefore, the heat.
Beautiful. You said it.
Not capturing all that.
Just
heat.
Right. It's kind of like a calculus problem. At the first step, you're getting hotter because you're getting closer to the UV light. But then you kind of get to a point where the number of absorbers starts to drop as the density drops. And then you can't absorb as much UV light because there's just less particles to absorb it. So it's a calculus problem where at first it goes up and then it goes down. That creates the stratospheric bump. Very nice. Very impressed with that. Okay, cool. By the way, let me show you a slide here and get you guys to put your noodle on this for a second. People consider the stratospheric bump to be a key signature of life on Earth, because as Jake mentioned earlier, the oxygen ultimately comes from life. And here's the story that we've put together over time about where Earth got its oxygen. Life began on Earth before there was an oxygen atmosphere. And that's in the form of single-celled organisms that probably formed near a hydrothermal vent in the ocean, eventually migrating their way up to the top of the ocean, creating blue-green algae, cyanobacteria, basically simple organisms that could do what plants do. They can absorb carbon dioxide and expirate oxygen. And over time, that oxygen starts to build up into a big layer on Earth because oxygen's heavy and Earth's gravity can hold it. But now along comes lightning bolts and ultraviolet light, breaking and sizzling apart O2, and now it forms a small layer of ozone, O3. And that ozone becomes like an ultraviolet bulletproof shield that now protects the surface land so that there's a lower flux of harmful UV light. Now life can actually creep up onto the land because there's oxygen for respiration and you're being shielded from the UV light. In a way, here's the most cool thing. Life has terraformed planet Earth to make it a happier place for life. Like, people talk about terraforming, we've done it right. And by we, I mean all of the gooey, squishy organisms on Earth. I'm putting us and the single-celled parameciums on the same sort of plane here, okay? We have collectively, as organisms, terraformed our planet. And by the way, we're continuing to terraform our planet and not always in a good way. Okay, so, but anyways, for the most part, life created the conditions for life to exist, which is just a really cool thing. For this reason, people think that if you could study the atmosphere of a planet outside of our solar system, if you could detect a stratospheric bump, a temperature layer, that might indicate that there was oxygen there, and that might indicate that there was life there. So people now see this as a measurable signature for the presence of aliens on other worlds. Double plus good if you're into aliens like I am. Okay. Let's say a couple words about the other layers, and then I'll, cancel, and then I'll try to end this at a reasonable time here. Let me just check my clock. We're doing okay. Almost done. I'll say a little less about each of these layers, and we'll get into the weeds on the next time. Okay, what can I tell you about the thermosphere?
It's warm.
Pardon?
It's warm.
It's warm. That's the, yes. Okay, let's start with that, Andy. That's correct. It's hot. But it's not only hot, it's thin up here, right? There's not a lot of gas. And what's happening is these gases are being heated primarily by those wicked short wavelength, wicked high energy X-rays. Here's the deal about X-rays. UV might be able to break apart a molecule, but X-rays don't just photodissociate molecules, they ionize them and rip electrons off. Let me share another cool slide from your book, which I think is worth talking about. It talks about the different ways that light can interact with gas particles, in our atmosphere, maybe somewhere around slide 20. Sorry, I'm just looking for the slide here. Here we go. So visible light is basically scattered, but is transparent to these molecules. Infrared light can get absorbed by greenhouse gases. UV light can break apart oxygen or water. We call that photodissociation. But when a wicked short wavelength X-ray hits a molecule, not only will it bust that molecule in half, it'll actually have enough energy to kick electrons right off the damned molecule. And do you know what that means? When you start kicking off electrons, you formed a plasma. And the thermosphere is actually partially in the plasma state. So X-rays, the word is photoionize, no D. X-rays photoionize gases. And that creates a layer of plasma, which we call the ionosphere. If you were taking a graduate level course in planetary atmospheres, and believe it or not, kids, this entire week's lecture could be expanded into a complete course, people would probably distinguish the thermosphere separate from the ionosphere. We're not going to do that. This is the wicked hot layer that's kind of in the plasma state. All right, that's how we're doing this. And remember that ionosphere, people sometimes equate it to being a layer of tin foil that surrounds Earth. The importance of it in the first place is, you know those FM radio signals we tune into in our car? FM travels farther than AM because you can bounce FM radio waves right off of the ionosphere. So this is how radio waves are propagated through great lengths across Earth, at least in the FM band. Because I'm running out of time, let's just make this our whole thing for the thermosphere for now. This is probably the layer of our atmosphere that we'll talk the least about, but it's quite interesting.
So Brendan.
Yeah.
Like, so the X-rays hit the particles, right?
Molecules of nitrogen and
The
oxygen.
molecules, yeah. So is that like fusion or fission in the sun? Because
no. Hold on, Joel. Let's get this straight.
Okay.
Here's an atom. There's the nucleus, right? And then going around the nucleus are some electrons. When you mess with electrons, that's just chemistry. You're kicking one or two of these guys right off your atom. You don't start talking fission or fusion until you start ripping apart the inner nucleus, which takes a way crazier amount of energy. X-rays can kind of, if they're high enough energy, can mess with the nucleus, but it's much less likely that that will happen. So no fusion, no fission, not the same thing.
Well, I was just thinking because like the helium, right?
Yeah, but
when they pair and they give off the electron or whatever.
remember this as well, Joel. The temperature needed simply for hydrogen fusion, which is the lowest temperature fusion possible, is 15 million Kelvin. Notice that our thermosphere is around 310 or 20 Kelvin. You ain't nowhere near temperatures needed for fusion. Okay, last little bit. Let's talk exosphere real quick, and then I'll let you guys go. Last layer of discussion is the exosphere. We're going to go into details on these next time. The exosphere is heated up a little bit by X-rays, but mostly the exosphere is heated by solar wind ions. You're so far out in space now that it's particles from the solar wind that heat you up. And I'd be lying if I said there wasn't a little bit of X-ray heating, but for the most part, your solar wind is a bigger heating source here. We define the exosphere as kind of like that layer where particles can undergo something called thermal escape into space. Basically, the exosphere is the layer that's constantly bleeding away into outer space. The other layers can't bleed away because they're too thick for the particles to jump off the planet. But there is always a few particles that are kind of boiling away into outer space. They can also get kicked off by solar wind ions. Also, we'll just say also solar wind, we call it stripping. We are kind of strip mining molecules from the atmosphere, albeit at a slow rate. Solar wind stripping removes gases as well. Basically, all planets have an exosphere because all planets with atmospheres have a layer where the atmosphere kind of just leaks a little bit into space. Atmospheres are leaky. That's okay because gas particles can be replaced by, wait for it, fresh volcanism. So one of the reasons why we think Mars's atmosphere is thinning the hell out today is you could see in your lecture last week that all of Mars's volcanoes were dormant. That means Mars is going to continue to leak particles slowly into space until there's not much left there at all. Earth and Venus still maintain thick, healthy atmospheres because it's definitely on Earth and presumably on Venus, we've got active volcanoes which can add to the gas. In our next lecture, we will learn some mathematical formulae for calculating thermal escapes and for considering how much heating an atmosphere gets. Next chapter, we get into some real microscopic stuff that's necessary to understand the big picture. But now you at least have a sense of layers of Earth's atmosphere and what makes one different from another. Okay, so let's check the time here. It's 12:53. I think that means we've done our duty with this lecture. A nice quick day today because remember, for anyone tuning in late, there's no lab, okay? I'm just talking to you about atmospheres. This stuff is very testable, though. On Wednesday, we have a lecture, and I'm still debating whether or not to give you a homework or not. I will make that decision at the very last moment when I start class, okay? It depends how far we get and what I think is healthy for the course. So guys, have a great day, and I will see you on Wednesday, okay? Live long and prosper. Bye-bye.